Hey guys, it's Dr. Turner here with ECET at Purdue University in New Albany, Indiana, and you're watching another video lecture series for 273 Modern Energy Systems. Today we're going over part 4 in our 4-part video lecture series on the use of AC power. Last video I had mentioned that we might turn this into a 5-part series, but that's not actually going to be the case. We finished it up in 4, so ignore those previous comments, and this is the last video lecture series for Module 2, AC power. So typically, when we deal with AC circuits, engineers and technologists were interested in calculations that involve the average value of voltage, current, and power in a circuit for reasons that we explained in the last lecture series. And to represent this average value, we use a term called the RMS, or the root mean squared measurement, right? And what you'll recall about RMS, or the RMS value, is that it's a measure of the sine wave's amplitude that's been scaled by the square root of 2. Well, why do we scale it by the square root of 2? Well, mathematically we showed that if we take the RMS value, we can use it to relate directly to the power that would be delivered by an AC source that's equivalent to the power that would be delivered by an DC source. So the use of RMS allows us to look at average power delivered over one period of a sinusoidal wave function and compare that directly to a DC source. They're equivalent, right? The VRMS and VDC end up being equivalent values. It's also important for us to know what the RMS value doesn't tell us about the sinusoidal quantity, which is the information regarding the timing of the sine function, right? We don't have any information when we know the RMS value about the frequency of the wave or about the phase of the wave. In most of power systems applications, frequency is taken as a constant across the system. For example, we've been talking a lot about the national frequency in the United States being 60 hertz and the national frequency in most European countries being 50 hertz. That's constant across the system. So what that says is that angular frequency omega, or the system frequency F, constant, 60 hertz in the US, 50 hertz in Europe. Therefore, when we're talking about voltages and currents in AC systems, we often take the frequency of that sine wave as a constant value. And then the only thing we need to represent a voltage, current, or power waveform in terms of its RMS value is the additional quantity of phase, right? We can eliminate frequency from the discussion because it's constant. Phase, however, and the RMS value aren't, so those are the two key pieces of information that we need to be able to relate voltage in a circuit to current flowing in the circuit to power delivered in that circuit. The technique that we're going to use in this class and in most of electrical and computer engineering technologies to represent sinusoidal quantities using only the RMS value in the phase is called phasor notation. It's one of the most common analytical techniques that you're going to encounter in electric power systems analysis. And we're going to begin today's topic by introducing the use of phasor notation, and we're going to derive it so that you understand why we can use it. We're then going to utilize the phasor technique to perform some calculations regarding the power in AC systems, and I think what you'll come to appreciate is how much simpler AC power calculations are when you use the phasor technique as opposed to representing sinusoidal quantities using the full sine and cosine expressions. So voltages and currents in the AC systems, as we have shown previously, are expressed as functions of time and are sinusoidal periodic functions. So for example, we might say that the voltage in a system as a function of time, so voltage is a function of time, V of t, and let's give it some arbitrary peak amplitude, 141.4 volts peak, right? Because that's the format for a sinusoidal quantity, is you put the peak quantity in there. And then remember the default in power systems, or the standard in power systems, is to use the cosine function, and then we've got the angular frequency times time. That gives us an angle plus 30 degrees. You'll probably recall that omega is usually in radians per second, time's usually in second, which means this is in the product of the angular frequency and time is going to be in radians, where the phase shift, phi, is commonly given in degrees. So, I can do something similar. Maybe I'm not interested in a voltage, maybe I'm interested in a current, right? So let's write a time domain expression for a current. So the symbol for a time domain is I of t. Again, these are time varying quantities, so we use lowercase in both instances. And then we're going to give it some peak current amplitude. We're going to go with 7.07 in this case. And then again, this is going to be represented by a cosine function, cosine of omega t. And in this case, we're not going to have any phase shift in the waveform. So in this notation, the maximum value or peak value of the current is 7.07 amps, and the maximum value or the peak value of the voltage is 141.4 volts, right? The RMS values then are found just by dividing these quantities by the square root of 2. So V peak, we would say, capital VP is equal to 141.4 volts. When we say VRMS is equal to 141.4 divided by the square root of 2. You'll recall the approximate value of the square root of 2 is 1.414. Pete Rose, as I've been saying in class. And this is going to give us an RMS value of 100 volts, excuse me. And we could do a similar calculation for I peak and or not of I peak, of IRMS, excuse me. And we would just do 7.07 again over the square root of 2 is going to give us IRMS. And that's going to be equal to, we'd see if we perform that calculation, 5 amps, right? So just again a demonstration of how we're going to represent time varying voltages as RMS and such things. You also recall that the RMS value is also called the effective value, as it gives us information regarding the average power delivered to a resistive load. And it's typically the value read by a voltmeter or an ammeter. So if I take out my trusty fluke and I measure the voltage delivered by an AC quantity to, let's say, a light bulb, it's going to give me an RMS reading. Flukes will, typically. And if I take that same thing and I interrupt the circuit and I measure the current, flowing to that light bulb, measure my current flowing to the light bulb, or measure the voltage across the light bulb, a fluke device, a fluke type multimeter is going to give me an RMS reading, what we would often call true RMS reading. So I also just want to remind you that when we write AC quantities, when we write the terms that are time variant, I of t and V of t, we use lowercase letters. And when we write the quantities, peak quantities, when we write RMS quantities, when we write instantaneous quantities, we use uppercase letters. So uppercase represent single quantities, where lowercase represent time variant quantities. And this is pretty much a standard technique in electrical engineering and engineering technologies that we're going to represent DC, instantaneous, and RMS values using capital letters. So if you see a capital letter, you know it's referring to it RMS, RMS or instantaneous or DC calculation. So to express the quantities that we wrote there, I of t and V of t as phasors, we have to choose a reference signal. The reference can be either of the signals that we included or some other signal. It can be some other arbitrary reference. What we'll see is important here is the difference between the phase of the reference signal, which we will always take as 0 degrees. That's why it's the reference. It has 0 degrees of phase shift. And the phase of the voltage and current functions to be expressed as phasors. What's important is the phase difference between the reference and those two, and the function that we're trying to represent as a phasor. So for example, if we were going to choose the current, the time variant current function as the reference phasor, we're going to write the time domain current expression in phasor form as I is equal to 5 at an angle of 0 degrees. Right? So you'll notice that 5 is the RMS value and 0 is the angle because we've chosen it as the reference phasor. And you'll recall from our discussion about complex numbers, the different formats, we could represent this not only in polar notation, but we could represent it in 5 plus J0, right? 5 plus J0. And both of these are in amps, so they should have units on it. The voltage that we saw earlier leads the reference phasor by 30 degrees and therefore has a voltage phasor form of V, capital V equals 100, again the RMS value, at an angle of 30 degrees, volts. And I could rewrite this in rectangular complex form as 86.6 plus J50. Now, if you're having trouble going from what we would call the polar form to the rectangular form, I encourage you to go watch the last video. Again, this is kind of an important step that you need to know how to be able to do, at least using a TI-89 calculator, if not understanding the mental math behind it. So what we can see here, what the big point is that the use of the phasor notation here, it's going to really reduce the amount of writing that we have to do when performing calculations involving the AC quantities. Before, we had to write, well, that's the RMS quantity. I think it was 7.07 or something. We had to write 7.07 cosine of omega t plus phi. We had to write all that stuff. And now we represent that same quantity as 5 at an angle 0 degrees. So we can really reduce the amount of writing that we have to do. It's just we have to be knowledgeable about what this phasor format actually stands for, right? So where do these phasors come from? Why can I use phasors to represent voltage and current? It is actually mathematically provable that we can use this phasor form to represent sinusoidal quantities, right? It's not just an engineering shorthand notation, it's valid mathematical notation. So what we'll say is that phasor notation is a shorthand way to characterize a sine wave, in that it specifies two things: the magnitude of the sine wave and the angle of the sine wave, right? Not the frequency, but the magnitude and the angle. Recall from our earlier discussions that sine and cosine, we can map them onto what we call the unit circle, right? That is, instead of tracing a wave that travels along the x-axis as we're used to seeing a sine and cosine wave, plotted like this, right? That's how we're used to formulating it. Instead of doing that, we can alternatively visualize a sine wave as a point that's rotating around a circle with a radius of 1 unit, and it's spinning around over and over and over again, right? And here, the x value of the, what is the name of that thing? The ray, the vector, there we go. The x value of the vector that connects from the origin to the point, the x component of that gives you the magnitude of the cosine function for that angle measured between the positive real axis and that vector, and the y component, if we were to decompose it down to the y, that gives us the sine function, right? So we've got the x value of a point rotating counterclockwise around the circle is represented by the value of the cosine function, where phi represents this angle formed between the vector from the origin to the point and the positive x-axis. And omega here is how fast this point is spinning, right? And we talked about this already. So because in AC power systems, we generally assume voltages and currents to have the same constant angular frequency, that frequency doesn't change whether this vector represents a voltage or a current, we typically ignore the counterclockwise rotation. We've got two vectors, right? We've got this vector, let's say this purple vector represents a voltage. We may have another vector that represents a current. And the point is what we're concerned with is the angle between them, because while they're both rotating, they're rotating at the same speed. Therefore, the angle between them, phi or theta, whatever you want to call it, remains constant. So thus we can indicate all the quantity as a fixed point on the circle, or more commonly as a vector pointing from the origin to that point. So really what we'll do is we'll represent phasor values using the positive real axis as the reference phasor. So the magnitude of the quantity is represented in this phasor diagram as the length of the arrow. So the length A here is the magnitude of the quantity. And the phase shift of the quantity is going to be the angle between the vector and the positive real axis. So this is phi, right? That's the phase shift of the quantity. So on the phasor diagram, which we're showing down here on the right, phasor diagram just refers to a picture that represents voltages and currents as phasor quantities. Here we see V of t is the reference phasor, and I of t is referred to the reference phasor. So on the phasor diagram shown down here, we've drawn the voltage as an arrow extending from the origin along the real axis, right? It extends from the origin in the positive real axis. And we're going to take it as the reference phasor in this case because it has a zero angle. This is very common, taking the voltage as the reference phasor. In reality, remember that for a sinusoidal quantity, this voltage phasor is spinning at a constant rate in a counterclockwise direction. But because we're only interested in the relative displacement between the two, we can ignore that spinning. So we're also going to remember that the length of this arrow represents the RMS value of the voltage. So we're going to draw the current phasor in relation to the voltage phasor, and it's particularly easy to do since the current lags the voltage by 30 degrees in reference to the time domain expressions that we had from the previous slide. We know that the current was 30 degrees behind the voltage. We're going to draw the arrow for the current such that it appears at an angle of minus 30 degrees in relation to the voltage vector. The length of the current vector also is going to indicate the magnitude of the current RMS. However, if we were to kind of make a comparison of the magnitude of the voltage and the magnitude of the current on here, while the lengths of them on this diagram are the same, we can't say that two equal length vectors indicate voltages and currents of the same magnitude. Why not? Voltages are measured in volts, currents are measured in amps, right? So we've got maybe 1 volt here. This is how many amps? You know, we can't really say because they're in different units, right? So the scales could be different because we're trying to represent two different quantities using one diagram, which means the scales could be different. So just because they're drawn to be the same length doesn't mean that they actually have the same RMS value, right? The utility of the phasor technique here is that we can combine any number of sinusoidal quantities on the same diagram in the complex plane as long as they have the same angular frequency. So as long as everything's rotating with constant omega, we can put as many different quantities on one phasor diagram as we want. And although technically complex impedances aren't phasors, we can use the same representations to include static quantities such as impedance on the phasor diagram, which is really nice. When we combine all these quantities into a single diagram, that later on is really going to aid us in performing complex mathematical operations using graphical techniques. So I know it seems easy to go from the cosine or the sine function directly to the phasor notation, 5 at an angle 0 degrees. But later on we are going to be solving circuits by representing voltages and currents as on phasor diagrams. So understanding how 5 at an angle minus 30 and 100 at an angle of 0 degrees, how they map to this diagram. You need to be able to understand that to participate in some of the conversations that we're going to have earlier. And one last thing that I'd like to point out is that this angle phi here is the phase shift between the voltage and current, right? In a resistive circuit, that would be 0. The only time we're going to see a phase shift in between the voltage and current is when we have some sort of complex impedance, right? When there's an inductance present, when there's a capacitance present in the circuit, right?